Today we're going to talk about the Earth and some interactions that it has with the sun to give us these things we call seasons. So most people understand, seasons, especially here in central Wisconsin. We have, fairly well-defined seasons of spring, summer, fall, and winter. That's not necessarily true everywhere in the world. As you get closer to the equator, typically the seasons are a little less well defined, but there are definitely changes throughout the calendar year where sometimes temperatures are a little bit cooler, generally speaking, or maybe certain times of the year are a little, there's more precipitation or less precipitation, things like that. So, what we are going to take a look at is why do we have these things called seasons? And what it really comes down to is the Earth's tilt. We've talked about that a little bit before in Earth science, how if you were to remove Earth's tilted axis from the equation, thinking of it kind of in math terms, that the Earth loses seasons. So if we remove the tilt, if Earth were spinning and it were spinning straight up and down, the sun would always hit this central region that we call the equator, and we would lose seasons. You wouldn't have spring or summer or fall or winter anymore. Throughout this entire trip around the sun, these seasons would always kind of remain the same. There'd be no variation. So what it really comes down to is the fact that if we take the tilt out of the equation and we lose seasons, well, then guess what the reason for those seasons is? It's Earth's tilted axis. So as we kind of look at this diagram here, I want you to notice a couple things. First up, the direction that the Earth is orbiting around the sun is kind of in this counterclockwise direction. That's important so you know kind of what season comes next. Once you figure out one or two of these, figuring out the remaining two is only possible if you know what direction the Earth is orbiting in the diagram. The other thing to kind of cue in on is where is Earth's tilted axis? So in this case, in this particular diagram, you can see how the axis is tilted in this orientation, and it's true in every single one of these pictures. The reason that's important is because we need to know where is the sun most focused, where is it most direct, okay? So the first thing you want to do when you're identifying seasons on a diagram like this is you want to find either summer or winter. For now, we're going to disregard fall and spring. We're going to focus just on summer or winter. So we'll kind of take a look at the season that we're heading to at this point in time, and that one is winter. So in winter, for us in the northern hemisphere, since Wisconsin is kind of right up in this region here, in the northern hemisphere, you can see how the tilt comes into play because the northern hemisphere is tilted slightly kind of away or tilted away from the sun. That means most of this sun's heat and light energy is focused in the southern hemisphere. And that's why when we have winter down here in the southern hemisphere, down in southern Africa and South America, Australia, they are experiencing the opposite season. All right, they're having summer down here while we're chilling out here in winter. And the reason for that is because most of the sun's heat and light energy is focused down here in the southern hemisphere. The little bit of heat and light that we do get, it's at a much lower angle, so it's not as focused. It's spread over a much larger area, and because of that, that reduces our kind of average daily temperature. So it gets colder. The more that happens, the colder it gets. So you can kind of see how the tilt comes into play there. If we jump over to the other side of the diagram over here, you can see how that situation is totally reversed. You can see how the tilt in relation to the sun, now that sun is kind of favoring or most focused on the northern hemisphere. Obviously, more heat, more light, that's going to raise your average daily temperature, and that's going to kind of create a climate where things are warmer, what we would call the summer season. Okay, so that only happens because in this orientation, kind of in this region of our orbit, the sun is most direct in the northern hemisphere. That means when we have summer, people down here in the southern hemisphere, they're experiencing just the opposite. They get a little less heat and light, and they experience that winter season. But up here in the northern hemisphere, what we're kind of focused on is the summer season right there. So if this is winter because of the tilt, and this is summer because of the tilt, well, then the only real difference between fall and spring is what season came before them and what season comes after them. So in this orientation here, if we can agree that this is summer in the northern hemisphere, we know that the orbit is moving in this counterclockwise direction. Well, after summer, we have fall, because fall is after summer and it's right before winter. So it kind of makes sense in this diagram, if we're going this way, that this one here is fall. And then when we come out of winter, head towards summer, we know that season there is spring. Otherwise, if these arrows were not present and we didn't know which way we were going, we really wouldn't, without guessing, be able to identify which of these is fall and which is spring, because the same exact thing is happening in each scenario. You have the sun during fall and in spring, even though you can't kind of see the daytime side over here. The sun is most focused on the equator. That means the sun's heat and light is split 50% in the northern hemisphere, 50% in the southern hemisphere. That means everything is equal as far as kind of your average temperatures and also amount of daylight. So everyone in the northern hemisphere, everyone in the southern hemisphere, in fact, everyone on planet Earth at the start of fall and the start of spring experiences 12 hours of daylight, 12 hours of nighttime, and kind of moderate or middle of the road temperatures during spring and fall, because the sun's heat and light isn't favoring either of the hemispheres. It's kind of right there in the middle on that line we call the equator. Okay, so that brings us to these particular times of year. The solstices are kind of the two extremes, what we looked at up here. We have a solstice in the winter, we have a solstice in the summer. Those two periods of time could not be any more different. They are about as polar opposites as you can get. So we have the summer solstice right around June 21st, and that ends up being our longest day of the year. What's actually going on there is, on a globe, if you've ever noticed, there's some other lines other than the equator that show up. One is called the Tropic of Cancer. Another one is called the Tropic of Capricorn. Those lines are important because during these solstices, that tells us where on Earth the sun is directly over. Where is it most focused? And during the summer solstice in the northern hemisphere, that is a day where the sun is directly over the Tropic of Cancer. It's exactly over that line, so that on noon or at noon on that particular day in kind of late-ish June, around June 21st, the sun is directly overhead at noon. Okay, straight up, 90 degrees overhead. So in the summer, we have that summer solstice on June 21. Then in winter, we go to December 21st or so. That, again, is the opposite, because the sun is now focused on this Tropic of Capricorn down here. So in our winter season, the sun is more focused in that southern hemisphere, and kind of the as far down as that sun gets focused is right here on the Tropic of Capricorn. And that happens right on or around December 21st. So that is our shortest day of the year in the northern hemisphere, whereas the summer solstice is the longest day of the year in the northern hemisphere. Okay? So then we have these other two events called equinoxes, and those happen once in spring and once in fall. So it goes along with kind of this part of the diagram here. So on those 2 days, actually the same exact event occurs. The sun is focused right here in the middle on the equator. So what I usually tell my students is when you think about an equinox, kind of think of these three words that start with the letters EQ. So when you have an equinox, the sun hits the equator, and that makes daytime and nighttime equal. So equinox, equator, equal. If you remember that, you'll be one step ahead of most. So what happens there is the sun is focused on that equator. That means half of its heat and light is focused on the northern hemisphere, half of it is focused on the southern hemisphere, and that is what kind of gives us our spring and fall seasons. Really, those two seasons are seasons only in name, because the same event is happening in spring that's happening in fall. You're just transitioning from one extreme, either winter or summer, to the other extreme. So the event is exactly the same though. The sun is directly overhead at noon on both those two dates. And what are those two dates? Well, it's kind of on or around March 20th or 21st, and then right around September 22nd or so. That's the only difference there is the date, but the event is the same. The sun is focused on that equator, and it splits everything up evenly, the heat and the light, all across the globe. So we have a little chart for you to fill out here, talking about what's going on, kind of some important things to be aware of for both of the solstices and the equinoxes. I'll give you a second just to kind of fill that out. You can pause the video here if you need to jot all that down. But basically, it's just going over where is the sun most focused. In the summer, it's in the northern hemisphere. In the winter, it's focused most on the southern hemisphere. What's the length of day? How is that impacted? Well, in the summer, it's longer. In the winter, it's shorter. Direct or indirect or equal amounts of solar radiation. It's more direct in summer. It's more indirect in winter. Equal in both spring and fall. And then the dates that I mentioned before. So you can see everything about the equinoxes is identical except the dates. The fall equinox happens in September. The spring equinox happens in March. So where that brings us next is this idea of solar altitude and solar azimuth. Okay, altitude, you may be familiar with that term about how high, like an airplane flies above the ground, or at what altitude maybe the peak of a mountain is. But in this case, solar altitude is how far off what's called the horizon. That's kind of ground level. If you're in a very kind of clear, open, flat area, that would be as far as you can see in every direction at ground level. That's called the horizon line. So what solar altitude is talking about is how far off that horizon line is the sun. And to measure that, we don't use like feet or miles or anything like that. We use degrees. So if you think of 0 degrees as being ground level, 90 degrees would be straight over your head. Those are kind of the extremes, because if you go past 90 degrees, then you're actually getting closer to the horizon line again. So solar altitude is talking about basically how high or how low in the sky is the sun. This height, the number of degrees, affects your overall temperatures. So here I'm talking about degrees in terms of an angle. Here I'm talking about temperature in terms of degrees Fahrenheit or degrees Celsius. Okay. Then we combine that with the idea of solar azimuth. That tells you basically how far to the north or the south or the east or the west is the sun located. And the way that we kind of talk about solar azimuth is also in degrees of measurement, again, not temperature degrees, but degrees of angle. And what we do is we take the cardinal directions and we turn those into degrees. So north is kind of our official start and end point. That's 0 degrees. If we turn 90 degrees to the right, we are facing due east. If we turn all the way around from north, 180 degrees, we find ourselves facing south. If we turn 90 more degrees, then we are facing west at 270 degrees from our original north orientation. And then if we continue on, we get back to north at 0 degrees again. So basically we took a full circle, we put cardinal directions on that circle, and then we just gave each one of those cardinal directions a degree measurement. So if we talked about the sun, say at 72 degrees of solar azimuth, then that would be kind of over in this region. Not quite due east, because that's at 90, but definitely not north and not any of these other directions. So 72 degrees of solar azimuth would put the sun kind of in this region, kind of in the northeast-ish corner. All right, so what does this help us do? Well, it basically helps us kind of identify where the sun is at certain times of the day and certain seasons throughout the year. It's kind of like a GPS tracker for the sun, is what I'm trying to say. So if we take kind of the left to right sort of orientation of solar azimuth, we take the height of solar altitude, we put those together, we can track exactly where the sun goes at the different points throughout the year. So is it going up higher? Is it staying down lower? Is it rising over here and setting over here, or in some different location? We can track the sun with the help of solar altitude and azimuth. Changes in solar altitude, basically the higher it gets, the higher the air temperature tends to get. And solar azimuth, we talk about in terms of kind of how wide or narrow it is. When you have a wider solar azimuth, that basically means the location where the sun rises and sets is further apart. That extends our hours of daylight, whereas in other parts of the year, the solar azimuth is very narrow. That means the location where the sun rises and sets is much closer together. That reduces our hours of daylight. And we're actually going to be working on an activity that looks at solar altitude and solar azimuth and how that changes throughout the year, throughout the different seasons, and see what effect solar altitude and solar azimuth have on the different seasons to kind of more fully explain the reason behind seasons.